Wow, fantastic. Mm. So we're going to eat. Mm. El nepotismo. Más el no nepota. El no nepota. Sí. El formulario de no nepota. Nepota. Sí. Que se me. O sea. Ah, no nepota. Nepota. Quita. Nepota. Nepota. No nepota. Hello, good evening, guys. Thank you for coming. Good to know that you guys are here. Thank you for coming on time. I would like to say hi. Let me see. I'd like to say hi to Carolina, to Jose Elias, to Karen, to Orlando, to Richard Alexis, to Talia, to Juan Sebastian, and Jenny. Thank you for coming, guys, on time. Okay, let's check what we have for today. Let's check our syllabus. So let's find our syllabus first. Where is our syllabus? Let's go check where is our syllabus. Let's check what is our syllabus. I think its syllabus is number 14, if I'm correct. Let's just wait for it. So today, hopefully we'll start a discussion on chemical reactors. So 2-3 sessions, 2 or 3 class times. And then we move on to our discussion regarding the economics of a chemical plant, which is very important for you guys. You guys will be complementing your project with the economic analysis. So you will end up having a techno-economic analysis. The technical part probably is well advanced by now. So the economics will be like a complement. Okay, let's see. There are some more people coming in. Okay. So we have our syllabus. Okay. Our syllabus. Let's go share syllabus. There we go. Okay, guys. Here we go. Let's see. Where are we? The computer is a bit slow today. Let's see. There we go. So after the midterm exam, we were directly involved in sharing or conveying, if we could say, topics regarding process heat recovery. Hopefully you guys were able, this is a very important topic because in industrial plants, what you want to do is save money. The amount of money paid in electric consumption in an industrial plant is just humongous. The amount of money paid for fuel, for bunker fuel, for diesel fuel, it's humongous. I'm saying this as I used to work in a instant soluble coffee processing company here in Guayaquil. Yo trabajé en el café casi 8 años aquí en Guayaquil antes que la empresa cierre. La empresa continúa laborando en la planta de Montecristi, pero tenía una planta aquí en Guayaquil al lado, al costado del City Mall. Cuando usted pase por el City Mall, va a ver una cuadra, eh, justamente en la entrada vehicular del City Mall. Al frente se ve pues una pared enorme sin mayor eh, mención, ¿no? Mención de qué puede hacer. Pero de un costado sí está la puerta de ingreso y ahí menciona que es la compañía de elaborados de café, el café, ¿no? Entonces ahí esa era una planta industrial, es una planta industrial, pero en aquel entonces hasta el año 14 era una planta que estaba laborando y se hacía pues eh, la fabricación de café soluble instantáneo. Entonces, de referencia de lo que escuchaba, no era mi, digamos, responsabilidad, porque yo estaba encargado en aquel entonces de la investigación y desarrollo de los productos en el café. Yo escuchaba de compañeros o de referencias o quizá de una de las autoridades los costos que tenía la empresa. Los costos eran simplemente una cosa exorbitante. Creo que me pasaría mi vida pagando algo así. Sí, eran unas cosas exorbitantes. Entonces, en la recuperación de calor, lo que se busca es justamente tratar de mitigar eso, ahorrar en lo posible en consumo de vapor, que hay una relación directa con el consumo de búnker y el agua de torre, porque de todos modos, aunque la torre esté estática ahí, hay que cuidar la torre, hay que cuidar que tenga el tratamiento de agua, cuidar que la bomba opere correctamente, si algo le pasa al hombre, hay que hacerle mantenimiento, hay que cuidar las torres vienen con el agua que chorrea, la parte que regresa del proceso, viene un poco más caliente y chorrea desde arriba con unos dispersores, ¿no? Eso tiene un nombre especial, no son jets, pero bueno, viene como unos difusores en la parte de arriba y llueve hacia abajo y llueve a través de unos empaques que son de material polimérico. Cuando viene muy caliente el agua, esos empaques se aplastan y ya simplemente se perdió esa capacidad de transferencia de masa. Entonces, a pesar que son equipos que uno los ve aparentemente fuertes, hay que cuidarlo, como todo en la vida hay que cuidarlo, si no se echan a perder, así como un caldero. Si no cuida usted el agua blanda, se incrusta todito y es un desastre. En fin, son solo comentarios, ¿no? Pero es extremadamente importante la recuperación de calor en una planta industrial real, una planta industrial. El día de hoy nos toca topar otro tópico. Si bien es cierto, no toda planta industrial tiene reactores químicos, como la planta del café no tenía un reactor, no tiene un reactor químico, la planta de Montecristi. Sin embargo, eh, hay plantas industriales que sí tienen reactores químicos. Es importante topar este proceso. Además, ustedes pueden estar haciendo alguna simulación que requiera un reactor químico y entonces hay que topar estos temas, particularmente situaciones de equilibrio, cómo la temperatura pues influencia en el desempeño de un reactor y cómo la presión influencia particularmente en la conversión de equilibrio de un reactor, modificaciones de temperatura, modificaciones de presión y creo que si al final mencionamos algo de concentración. Entonces, eso esperadamente compartimos, empezamos a compartir el día de hoy. Quiero darle saludar a los que acaban de ser unidos con nosotros. Gracias por unirse con nosotros y por compartir esta noche de este nuevo tema que vamos a tratar, que es el tema de reactores. Vamos a compartir la diapositiva y vamos a minimizarnos un poquito por acá. Muy bien. Entonces, okay, chemical reactors. Hopefully we'll cover today, just a good chunk of these. These are like 200 slides, but we will not cover the 200 slides today. That would be just too much. Hopefully we'll cover, maybe 60 of them as we make progress. Hopefully we'll cover all of these in 2 or 3 class sessions, virtual class sessions with you guys. Como por alguna razón esta barra se atasca, entonces lo que vamos a hacer es ponerlo en este modo no de presentación hasta que la barra suba y ahí lo podemos poner en modo de presentación. Uno de los efectos de tener un computador ya con varios añitos. Ok, nos dice, some of the important effects regarding reactions conditions will be considered in this discussion. However, before considering reaction conditions, some basic principles of chemical equilibrium need to be reviewed. Continuamos. Ok, ahí vamos. Tenemos una persona más y nueva presentación. Reactions can be considered to be either reversible or essentially irreversible. An example reaction of a reaction that is essentially irreversible is a ethylene reaction with chlorine to produce dichloroethane. An example of a reversible reaction is a hydrogen and nitrogen reaction to produce ammonia, which is also reversible to revert back to the reactants. For a given mixture of reactants at a given temperature and pressure, there is a maximum conversion, the equilibrium conversion, that cannot be exceeded and is independent on the reactor design. The equilibrium conversion can be changed by appropriate changes to the concentration of reactants, temperature, and pressure. The key to understand reaction equilibrium is the Gibbs free energy, or free energy defined as, and you will see, as you have seen in many of the slides on previous discussions, the citations for many of these statements, you will find them at the end. Usted va a encontrar las citas de lo que se va tratando en los diferentes temas de esta clase. Las citas bibliográficas ahí mismo al final en la parte inferior de la diapositiva, ¿no? Tenemos un camión de Puerto Limpio aquí afuera. Esperemos que no tome mucho tiempo, ¿no? Normalmente no toma mucho tiempo. Okay, so the key to understand reaction equilibrium is the Gibbs free energy defined by equation 6.3 as Gibbs free energy is defined as the enthalpy minus the temperature in kelvins times the entropy, and then you see the definition right there. This is, I'm sure you guys are aware of this from thermodynamics, so just go on. A negative value of delta G implies a spontaneous reaction of reactants to products. A positive value of delta G implies a reverse reaction is spontaneous. This is illustrated in figure 6.1. A system in equilibrium when it is in equilibrium when delta G is equal to 0. This is what we see here in this figure 1. We are continuing this topic on reactions from the book of Robin Smith. So that's why you see the citation of Robin Smith. If I'm correct, this is chapter 6. That's why you see figure 6. And the examples, they start with the number 6 because it's chapter 6 from Robin Smith's book. Okay, yeah, Brian. Okay, so when delta G is less than 0, so there is a change in the Gibbs free energy of a given reaction is less than 0. That means there is a spontaneous reaction of reactants to products. When the reaction is in equilibrium, delta G is equal to 0. When the change in the Gibbs free energy is the magnitude is over 0, is greater than 0, then it's a spontaneous reaction of products to reactants. So it's reverting back into reactants. The free energy can also be expressed in differential form. That is according to equation 6. That will be the differential of the Gibbs free energy will be minus the entropy times the differential of the temperature plus this is the volume, molar volume, if I'm correct, times the differential of the pressure, where V is a system volume or system volume. At constant temperature, dt is equal to 0 and equation 6.6 becomes, as you see in expression 6.7, so this term goes to 0. For n moles of an ideal gas, PV is equal to nRT. See that in this case, they define n, the number of moles, with a big N. Some books have n with a small n, but in this particular book, n, the number of moles, is defined with a big N. So PV is equal to nRT. You guys are familiar with this from, just general chemistry class, where R is a universal gas constant. Substituting this in equation 7, then we obtain this expression for equation 8. What we're doing is reviewing the different equations and then finally make an emphasis of the important questions in this group of discussions on chemical reactors, just a few important questions, and then do exercises using those important questions. Also, whenever you guys turn in homework number 4, you guys will receive the last homework number 5. And that homework, I believe, is it homework number 5, where you guys will receive the homework regarding AICHE, the safety course, whichever comes first. Maybe that's first, and then, yes, I think that is first, and then you will receive homework number 5. So homework number 5 will hopefully contain not only material on chemical reactors, but also will contain problems regarding the economics. So by then, hopefully we have already covered topics on economics plus topics on chemical reactors. So you guys are, you can practice that in the homework. Also in the exam, you have all the necessary formulas, so you don't need to memorize all these formulas, but this is just like a reminder of where the main formulas come from, and then we'll just stick with the main formulas and use the main formulas for examples in class, in this virtual class, and also when we send the homework, they will be related to the main formulas that we make emphasis during the class. Okay, so the equation 6.8 gives pass, if you can say, ends up being equation 6.9 for the change in pressure from P1 to P2, and after can be integrated. This is in terms of an integration, so it's being integrated on the left and on the right, and it will end up being this expression on the right. So the integral has not been, let's say, carried out yet in equation 6.9. Values for free energy are usually referred to the standard free energy, G with a 0. It looks like to the power of 0, but it's just that 0 on top means that is at standard conditions, gives free energy at standard conditions. The standard state is arbitrary and designates the datum level. A gas is considered here to be at standard state if it's at a pressure of 1 atmosphere or 1 bar for the designated temperature of an isothermal process. Thus, integrating equation 6.9 from standard pressure to a given pressure P. So if this expression to the right of this equation is integrated from standard condition, the pressure at standard conditions, to a given pressure, a final pressure, then that will give, hopefully this equation will be obtained, equation 6.10. So that will be a number of moles RT, which are constants, and the natural log of P, and natural log of the difference, that will be, natural log of P, and the difference between P2 and P at standard conditions is what produces P over P at standard conditions. This G sub 0 would be one of these conditions, G1, my guess. So G2, G will be obtained as the sum of G at standard conditions plus this ratio of pressures, natural log of this ratio of pressures, times the constants of number of moles R and T. So this G1 will be moved to the right, and we are solving for G2, which is called here just G in equation 6.10. For a real system, rather than an ideal gas, equation 6.10 is written, you might remember this in terms of fugacity, and fugacity is standard conditions from thermodynamics. Just a few weeks ago, maybe it was like last week, we were discussing a topic regarding fugacity in our thermodynamics class, exactly like that. So you might remember this from thermodynamics. So instead of pressure, final pressure over pressure standard conditions, now this is expressed in terms of fugacity, where F is the fugacity expressing Newton per square meter or bars, and fugacity standard conditions is also Newton per square meter. So Newton, if I'm correct, it has to be divided by a square meter. So I'm not so sure if this multiplies square meter, because Si son unidades de presión, usted sabe que un newton sobre metro cuadrado es un pascal y 100.000 pascales es un bar. Y entonces mi sospecha es que esto realmente es newton dividido para metro cuadrado o multiplicado para metro a la menos 2. Eso tiene que estar dividido porque eso es un pascal, ¿no? Es unidad de presión. Y la fugacidad nos da unidades de presión. Eso entendemos nosotros. Entonces, ambas, aquí tiene que ser un término adimensional, newton por metro cuadrado. Decimos por metro cuadrado, pero en realidad es dividido para metro cuadrado. Y acá igual newton dividido para metro cuadrado en condición estándar. Esto debe dar eh, esta división adimensional por completo. De modo que se multiplica por nRT y las unidades aquí coinciden con las unidades de la energía libre de Gibbs, que estarán, que estoy correcto, en kilojoules, ah, en unidades de energía. ¿Mm? Kilojoules, menos que sean kilojoules por tiempo, ahí tienen un puntito encima, pero en este caso serían unidades de joules o kilojoules, megajoules o algo así. Muy bien. F is fugacity, F subs with a zero. On top is fugacity, standard conditions. A is activity, which is the ratio of F over F sub zero. Not sub zero, but F with a, zero on top. Okay. And you can notice that this has been set equal to just the natural log of the activity. So activity is being taken as the ratio of F over F with at standard conditions. The concept of fugacity and activity have no strict physical significance, but are introduced to transform equations for ideal systems to real systems. Es una medida de llevar una reacción de las condiciones de idealidad a una condición real. Y básicamente por eso se utilizan los términos y los conceptos de fugacidad y de actividad. Eso es justamente lo que estábamos viendo los estudiantes de termodinámica 2. Cuando ya un sistema de parte de o se aleja de la condición de idoneidad, de idealidad, perdón, como por ejemplo usando la ley de Raoul, que la ley de Raoul depende, o más bien se basa en la suposición que el gas es ideal y que la solución es ideal. Cuando esa situación está departiendo de la idealidad, se usa el coeficiente de actividad, que es gamma sub i. Ustedes quizás recordarán esto de termodinámica, ¿no? Más adelante se trata de los términos de fugacidad, el coeficiente de fugacidad, de las ecuaciones de Soave-Redlich-Kwon, de Penn-Robinson, que son ecuaciones de estado, que utilizan una ecuación cúbica para su determinación. Entonces, justamente se utilizan cuando el sistema que está en equilibrio está departido, está en condiciones de temperatura y de presión, que no son exactamente las condiciones similares o próximas de un gas ideal. Entonces se utilizan este tipo de términos para tratar de predecir el comportamiento de equilibrio gas-líquido cuando un combinado, digamos, binario, un par de componentes que están en un sistema en equilibrio, vapor líquido, ha departido de la idealidad. Básicamente para eso es que se utilizan los términos y los conceptos de idealidad, fugacidad, eh, eh, coeficiente de fugacidad. However, it does help to relate them to something that does have physical significance. Fugacity can be regarded as an effective pressure, and activity can be regarded as an effective concentration relative to a standard state. Consider the general equation B times B plus C times C is equal to, so this is like a reaction, and this is the small letters are the number of moles, and the big letters, they represent, I'm not so sure if they represent the different compounds in the reaction. Equation 612. The free energy change for the reaction is given the change in the Gibbs free energy would be the products minus the reactants. And that's why you see the product, the small, which is the number of moles, is stoichiometric number of moles in equation 612, times what we see here, this G sub S with the bar on top, which means the partial molar free energy of component I in kilojoules per kilomole. So times kilomole, the change in the Gibbs free energy The units will be in kilojoules, just like you see right there. So that will be number of moles times kilojoules per kilomole, so the partial molar free energy of component I. So this will be of the components of the products minus the components of the reactants, just like you see right there. And at the end of the day, you'll have the reaction will be in the units of kilojoules. Note that the partial molar free energy is used to designate the molar free energy of the individual component as it exists in the mixture. This is necessary because, except in ideal systems, the properties of a mixture are not additive properties of the pure components. As a result, for a mixture, the Gibbs free energy of the mixture is equal to the summation of I. N is the number of moles of component I times the partial molar, just like it says here, partial molar free energy of component I in kilojoules per kilomole. So that means that the Gibbs free energy of a given reaction at the end of the day is a result of how much each individual component is contributing to the Gibbs free energy. So components that have a greater number of moles, we have a greater contribution into the magnitude of this parameter. Pretty much that's what this equation is telling us. So let's say you have a very small stoichiometric coefficient, small number of moles for a given component. So that will have a small participation in the summation, small participation in the magnitude of G at the end of the calculation, pretty much. And a component that has a big amount of moles, very large amount of moles, then we have a big participation because it's, as it seems in here, it's just a summation of participants of products and reactants of a given reaction. The free energy change for reactants and products at standard conditions is given by very analogous to what we saw in this case, equation 613, products minus reactant. So the number of moles times, in this case, the partial molar free energy of component I at standard conditions, again in kilojoules per kilomoles, times the number of kilomoles per specific compound. So delta G standard conditions will be again in kilojoules. Question 14. So now we have equation 13 minus 14, the results of equation 13 minus the results of equation 14 will be expressed in equation 15. Writing equation 11 for the partial molar free energy. Let's say we find equation 11 here somewhere there. So writing this equation or this equation in terms, it says in here, for the partial molar free energy of component I in a mixture, then partial molar free energy of component I minus partial molar free energy of component I standard conditions is equal to RT ln of the activity of component I. So that could be replaced in this, differential difference that could be replaced in each one of these different components. And then we probably end up with equation 17, where you see the difference in the partial molar Gibbs free energy of component I minus the partial molar Gibbs free energy component at standard conditions. You'll see that RT ln AS, RT ln AT, RT ln AB, RT ln AC. That's what you see in equation 17. Again, products minus reactants. And this is what we see S, that's what we have here, S ln AS, T ln AT, B ln AB, C ln AC. Okay, so since S ln AS is equal to or has an equivalence to ln A to the power of S sub S, so ln A sub S to the power of S, so this is equivalent to this. And also T ln A sub T is equal to L ln A to the power of T sub T. Then equation 17 could be rearranged as we see there. with the new definitions or the equivalent definitions and express right there. That will be products minus reactants. So we have a big division numerator, all the products multiplying each other. RT is constant, so that could be taken out. So RT ln of products, so that will be ln a to the power of s sub s. So ln will be outside, a to the power of s sub s times a to the power of t sub t, etc. All the products and the reactants that will be in the denominator, the a to the power of b sub b times a to the power of c sub c, as we see right there. Transform, so equation 617 becomes 618, because of this equivalence. Now, note that rearranging s ln as to ln a to the power of s sub s, the units of RT ln a to the power of s sub s remain in kilojoules. And this expression, a to the power of s sub s, is dimensionless. So this ratio will be dimensionless. And the units of delta G standard conditions will be the units of R times T. So R is expressed in what? Kilojoules. This is the universal gas constant, 8.314 joules over mole per Kelvin, if I'm correct. So if we're multiplying Kelvin, but it's going to end up being joules per mole or something like that. So it seems joules per mole. So this expression, which is this expression 618, will end up being equation 619, where K sub A has this definition 620. K sub A is known as the equilibrium constant. It represents the equilibrium activities for a system under standard conditions and is a constant at constant temperature. So for homogeneous gaseous reactions, substituting for the fugacity in equation 620 gives us this expression, which is also equivalent to the fugacities, because remember, the activity is equal to the fugacity over the fugacity at standard conditions, just like you see there. So the activity of S to the power of S sub S would be equal to the fugacity of S to the power of S sub S over the activity of S at standard condition to the power of S sub S, just like you see right there. And that would be multiplied times the activity of the fugacity of the equivalence to the activity of T, which is fugacity of fugacity standard conditions for T and for all the products. And that should be divided by the fugacity of the reactants. And since it is being divided right there in the denominator, it's like you can multiply this with an inverse, so that the fugacity of the power of B sub B would be in the denominator, and in the numerator you have the fugacity standard conditions of B sub B, since you are dividing all these terms by the equivalence of this term, which is fugacity or fugacity standard conditions. That's why you have them inverted right there. And that's why it ends up being equation 621. So for homogeneous gaseous reactions, the standard state fugacities can be considered to be unity. That is, the fugacity standard conditions is 1 for a homogeneous gaseous reaction. And so we have equation 622, where F sub I is fugacity of component I, phi sub I is fugacity coefficient of component I. You might remember that fugacity coefficient is obtained with the equation of state. Suave, Presley, Kwon, and Penn Robinson. And there are a series, we were reviewing that this week with the students of thermodynamics, a series of equations to calculate using the, either way, you can use Suave, Presley, Kwon, Penn Robinson, but there are many equations that need to be small calculator. You have to calculate A, B, A prime, B prime, in order to obtain the fugacity coefficient. Well, once a fugacity coefficient is obtained either with the Suave, Presley, Kwon, or Penn Robinson, then you can use that value right there. And P sub I is a partial pressure of component I, and then the fugacity of component I will be obtained. Substituting equation 622 into equation 621. So remember that we had the question 621 in terms of the fugacity. So now, since this concept, this expression was introduced, so everything now will be in terms of the fugacity coefficient and the partial pressure of every component. So equation 623 is a result of replacing 622 into 621. So we have this big expression. The fugacity is on the expression here on the first expression on the right-hand side, and then the partial pressures on the second expression on the right-hand side. So this has been defined as K sub phi, K, the equilibrium expression for the phi components, times K sub P, that is equilibrium expression for the partial pressure components, that will be expression 623. Also, by definition, the partial pressure is equal to the mole fraction in the gas times the system pressure. Mole fraction of component I times the system pressure. So this could also be expressed. So this term could also be expressed in terms of YIP. So it will end up being something like this in terms of the mole fractions in the gaseous phase times P, the delta N. That is, delta N will be the number of moles stoichiometric reaction in the products minus the number of moles in the stoichiometric reaction of the reactants. And so you have the system pressure to the power of whatever that difference might be. So Ka will end up being K sub phi, as you see there, K sub Y, as you see there, times the system pressure to the power of the difference of the number of moles of the products by the number of moles of the reactions of that specific reaction, where delta N is S plus D, the number of moles in the products according to stoichiometry, minus the number of moles of the reactants. So in ideal conditions, for an ideal gas, phi sub I is 1. So that would be fantastic. This whole term ends up being 1. So we're only left with the partial pressure of the different components in this equation, at least. If the first expression to the right ends up being 1, we're only left with this expression. But this expression can be also expressed in terms of Yi and the system pressure. So 626 ends up being 627. So we have the mole fractions in the gaseous phase for products over reactants times the system pressure to the power of delta N according to this definition. So we have 627. This will be the equilibrium expression for the reaction. For a homogeneous liquid reaction, the activity can be expressed as activity sub I is equal to gamma sub I. Remember we mentioned gamma. Gamma is introduced when the conditions of a given reactions in the gaseous phase depart from reality, depart from ideality. So A sub I is the activity of component I, gamma sub I is the activity coefficient of component I, and X sub I is mole fraction of component I. So activity coefficient in equation 628, which is gamma sub I is equal to A sub I over X sub I, can be considered to be the ratio of the effective to actual concentration, because the units of AI and the units of X sub I, it would be the same. So you end up having some ratio of dimensionless also. So substituting 628 into equation 620, substituting this equation 28, now in terms of the activity coefficient, component I, and the mole fraction in the liquid phase of component I, substituting that into equation 20, which is, let's say where we find equation 20, this equation. So going back all the way when the equilibrium constant was defined in terms of the activity coefficients of products over reactants. So in that equation, if we replace 628 into this precise equation, then we will end up with equation 29. So now is in terms of the activity, what is this activity coefficient of the products over reactants times the mole fractions of products over reactants. So the equilibrium expression Now it's defined in terms of K sub gamma times K sub X. For ideal solutions, activity coefficients are unity, so the whole term turns to 1. So we also have a expression 630. So for liquids in ideal solutions, this will be the correct expression to use. And for gases, at ideal conditions, this will be the correct expression to use depending on different reactions. If the reaction is in the gaseous phase, this will be the correct equilibrium expression to use. If the reaction is in the liquid state, then this will be the correct equilibrium expression format to use. Heterogeneous reactions. For a heterogeneous reaction, the state of all components is not uniform. For example, a reaction between a gas and a liquid. This requires standard states to be defined for each component. The activity of a solid, the equilibrium constant can be taken to be unity. Consider now an example to illustrate the application of these thermodynamic principles. Tenemos el ejemplo 1. Esperadamente lo hacemos, lo terminamos. Y los otros ejemplos los hacemos aquí o los vemos aquí en diapositivas y vemos también cómo lo proyectamos en Excel para que ustedes también vayan viendo en sus tareas cómo van usando el Excel, ¿no? El Excel es una herramienta y no podemos obviarla, ¿no? Incluso mis estudiantes de termodinámica están utilizando el Excel porque llega un momento que se vuelve un poco complejo realizar tanto cálculo en termodinámica. Entonces aquí, como estamos haciendo una revisión de varios temas, van a llegar ciertos ejercicios que requieren, por decir, el CP en términos de temperatura, que tiene varios términos y tiene coeficientes, y se vuelve un poco engorroso hacer los cálculos manuales, que se pueden hacer, pero ya es engorroso. Pero teniendo la herramienta de Excel la podemos utilizar, ¿no? Esa es la idea. Estos primeros ejemplos, el primero es sencillo, relativamente sencillo, y los otros pues van requiriendo mayor uso, mayor dependencia del Excel. Okay, example 6.1, a stoichiometric mixture of nitrogen and hydrogen is to be reacted at 1 bar. So we have this reaction. It's a well-known reaction of hydrogen and nitrogen to produce ammonia. It's a reversible reaction. Assuming ideal gas behavior with this definition of R, 8.314 kilojoules per kilomole or 8.314 joules per mole per Kelvin. That would be pretty much the same. Calculate the equilibrium constant, the equilibrium conversion of hydrogen, the composition of the reaction products at equilibrium. So the first thing it is asking for is the equilibrium constant. Okay, so that will be K sub A, pretty much that's what it's asking. Then it's asking for the conversion, the X, which is a conversion of hydrogen of this reactant, and the composition of the products at equilibrium. Okay, so at 300 Kelvin, standard free energy of formation data are given in table 615 according to, it seems that this is CRC press. So this is a reference book, the handbook of chemistry and physics. Maybe you guys have seen this. It's a very well-known reference book where you will find just a multitude of different values of different parameters at different conditions when you're looking for them to do some kind of calculation. This is a fantastic book, the 84th edition. Okay, this 2003 edition. I think they have an edition every year or something like that. And this book, of course, Smith is citing this 2003 handbook because the edition of this Smith book was 2005. So he's citing a previous edition. But if today you want to buy this, you probably buy the 2023 edition. So a lot more updated edition. So at 300K, standard free energy formation is given by this table, taken from the Handbook of Chemistry and Physics. That means that standard give free energy, sorry, as you see there, standard conditions in kilojoules per kilomole for hydrogen is 0, for nitrogen is 0, and for ammonia is minus 16,223 kilojoules per kilomole. Setting both equations, so we have the reaction where the change in the Gibbs free energy at standard conditions is the products, that would be the number of moles according to stoichiometry times the partial molar Gibbs free energy at standard conditions for ammonia minus the number of moles according to stoichiometry of the reactants, times the partial mole that gives free energy of hydrogen, minus the partial mole that gives free energy of nitrogen times the stoichiometric coefficient, which is 1. This is also equivalent to minus RT ln Ka, as we previously saw in one of the previous derivations. So these two, that mean delta G standard condition is equal to this products minus reactants, but it's also equal to minus RT ln Ka. So you can set these two equal to each other and solve for ln Ka. Then you would have ln Ka is equal to this operation right on the numerator divided by RT. And then you have this big negative sign because the negative sign came from this second expression. So now solving, knowing that you have what? Products minus reactants. The reactants are 0 according to this table, 0 for hydrogen and 0 for nitrogen. You only have give free energy, partial mole gives free energy, 300 K for ammonia. So that's what you replace there, the 16,220 negative sign times what? Minus 2. So you have minus 2 times 16,223 divided by RT. This is at 300, so 8.314 times 300. So the result will be 13.008. So the inverse of a log function will be the exponent of this. Here will only be Ka. The exponent to this result in the right will be 4.45 times 10 to the 5th power. So that could be set equal to the equilibrium expression. So the first thing that this problem was asking was the equilibrium constant. So the equilibrium constant defined as Ka is equal to 4.4597 times 10 to the 5. So that will be the result of the first literal A. Also Ka, by definition, will be equal, the equilibrium expression will be equal to the partial pressure of ammonia squared. This comes from this expression. So that would be the partial pressure of ammonia squared given to the stoichiometric coefficient there, divided by the partial pressure of hydrogen to the cubic power times the partial pressure of nitrogen to the first power. And that's what you see right there. Note that while Ka appears to be dimensionless, I'm sorry, it is actually dimensionless, since the fugacity of component I standard conditions is equal to 1 bar. Note also that Ka depends on the specification of the number of moles in the stoichiometric equation. For example, if the stoichiometry is written as in fractions, you see, written in fractions instead of written in whole numbers. So you could write these in fractions, 3/2, 1/2, and then it's just 1. As you see in the 3/2, 1/2, and just 1. Then that will affect the definition of Ka. So for a second definition of Ka, an equivalent definition, let's just say Ka prime, then you will have the products to the power of 1 over hydrogen to the power of 3/2 times the partial pressure of nitrogen to the power of 1/2. So you have this different way of expressing the equilibrium expression. So B is asking, once again, let's check on B, the equilibrium conversion of hydrogen. Yeah, so that would be X, the equilibrium conversion for hydrogen. Okay, so for part B, the number of moles and the mole fractions initially at equilibrium are given in table 6.2. So let's see, this is table 6.2. So you have in this table, you set this up, the products on top, hydrogen, nitrogen, and then the reactant also. The initial number of moles in the mixture according to a stoichiometry, you started with 3 for hydrogen, you started with 1 for nitrogen, and 0 for ammonia, because there was no production of ammonia. You started the reaction only with the reactants. At equilibrium, you will have 3 minus 3x, 1 minus x times 2x. This 2 comes from the stoichiometry, the number of moles of stoichiometry for the product. So at equilibrium, what you do, you add all this up. So you have what? Minus 3 minus x is minus 4x plus 2x is minus 2x. And the numbers are 3 plus 1 is 4. So we have 4 but minus 2x. And that's what you see right there. And this is what it you saw. The mole fractions at equilibrium, just like you see there, are divided by the summation of all of this. So the mole fraction of 3 minus 3x, or 3 times y minus x, is divided by the summation of these expressions, which is 4 minus 2x. The same is done for nitrogen. The same is done for ammonia. Well, so we have, then we have the expression in terms of the mole fraction in the gaseous phase times the system pressure. And the expression will be the mole fraction of ammonia squared, the mole fraction of hydrogen to the cubic power times the mole fraction of nitrogen to the first power times the system pressure to the power of delta N. Delta N will be products minus reactants, that'll be 2 minus 4 is minus 2. So P will be to the power of minus 2. But the system pressure is 1 bar. So regardless of the coefficient, the power of the system pressure, it's just 1 to whatever power that is. And you will also have the result of that will only be 1. So at the end of the day, we will only end up with this expression for this reaction that operates at 1 bar. So Ka, notice that Ka is in terms of this individual expression for the different components of the ammonia reaction. So we'll have 2x over 4 minus 2x squared right there. And in the denominator, we will have 3 times 1 minus x divided by 4 minus 2x times 1 minus x divided by 4 minus 2x. And the first expression will be to the cubic power. So solving for all of that, we'll end up with this expression on the numerator and this expression for the denominator. Notice that the whole expression right there is to the cubic power, while the expression for nitrogen is to the first power and the expression for ammonia is squared. So we'll end up with all this expression. I think this cubic power should be outside. I have to correct this. Okay, so we'll end up with the expression that is here on the right. So at 300 K, what is being set equal is a result from part A, which was Ka, the result from part A. That is equal to the simplification of the equilibrium expression, which is this expression right there. 4.45 times 10 to the 5th power is equal to this expression, which is expression for the equilibrium of that particular reaction. And solving by trial and error using Excel, most likely, X comes up to be 0.97. So you replace a guess value on X until you obtain the same number that you see on the right, you obtain the same number. I'm sorry, the same number that you see on the left, you will see the same number on the right. So you keep on using a guess value between 0 and 1 until the expression of the magnitude of the number in the right is equal to the magnitude of the number on the left. So now the concentrations of the molar fractions of different components can be found, and they all come from their individual expression. So these results come from using this expression and replacing that with X is equal to 0.97. So they were asking for the equilibrium conversion and finally the composition of the reaction products at equilibrium. So the composition, this will be the conversion and that will be the composition for the individual components. It says here some points should be noted from this example. Firstly, ideal gas behavior has been assumed. This is an approximation, but it is reasonable for the low pressure. Remember, this all occurred at 1 bar, or apparently it occurred at 1 bar. It is reasonable for the low pressure assumed in the calculation. Later, the calculation will be repeated at higher pressure when the ideal gas approximation will be poor. En este caso es cuando ya se empiezan a usar otro tipo de aproximaciones cuando nos estamos alejando de las condiciones de idealidad, lo que comenta aquí. Also, it should be clear that the calculation is very sensitive to the thermodynamic data. Errors in the thermodynamic data can lead to significant different results. Thermodynamic data, even from reputable sources, should be used with caution. Que si tenemos datos termodinámicos que hemos usado, por ejemplo, si hemos obtenido la energía libre de Gibbs, para alguno de los componentes tenemos otra reacción y hemos tomado un número equivocado para uno de los componentes de la otra reacción, todos nuestros cálculos van a estar errados. Entonces nos dice que nos aseguremos que los valores que estamos obteniendo vienen de fuentes confiables, ¿no? Por eso dice reputable sources, que los datos termodinámicos, como veíamos al inicio de este ejercicio, que nos proveyeron los datos termodinámicos, que estos valores estén correctos. Mire usted que cómo se han expresado. Nosotros usaríamos una coma justamente para luego expresar fracciones de un entero, ¿no? Nosotros, aquí en nuestro medio. Pero ya se usa una coma en los libros para hacer énfasis en la magnitud de miles, ¿no? Y usted ve que es una magnitud de miles porque al reemplazar el valor aquí, la ecuación para LNKA, aquí están los miles, 16.226, 223 y no 16,223, como usaríamos. Entonces, ojo, que si en un examen aparece una cantidad 200.000,351, eso, perdón, 200,351 para energía expresada en kilojoules por kilomol de un compuesto X, está haciendo referencia, tenga presente que muy probablemente se está refiriendo a miles, no a fracción de 200, ¿no? Si usted tiene 200,351 en un listado de energía libre de Gibbs para un componente X o un componente Y, son miles, no son cientos. Y eso me ha tocado hacer énfasis durante un examen para que los estudiantes tengan claro y no, si no van a estar errados por un factor de 1000, básicamente van a estar errados por un factor de 1000, o la respuesta no va a tener sentido. Ok, llegamos hasta acá. ¿Qué más podríamos ver para concluir hoy? Esta de aquí. Sí, yo creo que hasta ahí podríamos llegar, porque luego tenemos reactor temperature. Okay, nos dice equation 619 can be interpreted qualitatively to give guidance on the equilibrium conversion. If delta G standard conditions is negative, the position of the equilibrium will correspond to the presence of more products than reactants. Ln Ka is greater than 0. If delta G standard conditions is positive, Ln Ka is less than 0, the reaction will not proceed to such an extent and reactants will predominate in the equilibrium mixture. Table 6.3, which is this table, represents some guidelines as to the composition of the equilibrium mixture for various values of delta G standard conditions and the equilibrium constant. This is equation 619 that was mentioned here. So here we see that when delta G is negative, Ka has big values. So the more negative it is, or the higher the magnitude of the negative number, the higher the magnitude of Ka in the positive. This means that negligible reactants products dominate. This reaction moves really fast towards the product. The opposite occurs when delta G standard conditions is positive. So the higher the magnitude in the positive number, the smallest Ka we will have. Reactants dominate negligible products. When delta G 0 is equilibrium, exactly at equilibrium conditions. When setting the conditions in chemical reactors, equilibrium conversion would be a major consideration for reversible reactions. The equilibrium constant Ka is only a function of temperature, and equation 619, which is this equation, you see that it's only a function of temperature, says equation 619 provides a quantitative relationship. However, pressure change and change in concentration can be used to shift the equilibrium by changing the activities in the equilibrium constant, as will be seen later. Finally, a basic principle that allows a qualitative prediction to the effect of changing reactor conditions on any chemical system in equilibrium is the Chatelier's principle. Yo les animo que se aprendan este principio, porque es un principio práctico para tener una idea de hacia dónde va girando el equilibrio. Probablemente ya lo han visto en cinética de reactores y es como un recordatorio de varios temas. Hemos visto diferentes temas. Les animo a que se aprendan, por favor, este principio que nos dice, if any change in the conditions of a system in equilibrium causes the equilibrium to be displaced, the displacement will be in such a direction as to oppose the effect of the change. Le Chatelier's principle allows changes to be directed to increase equilibrium conversion. Now consider the setting of conditions in chemical reactors. Esperamos, Dios mediante el próximo martes, continuar con la discusión de reactores químicos. Les agradezco a cada uno de ustedes por estar presente. Les deseo un excelente fin de semana, jóvenes, y nos vemos, Dios mediante, el próximo martes. Recuerde, el próximo martes hay que entregar la tarea y se enviará la próxima tarea, que lo más probable es el entrenamiento en la página global del AICHE, y todas las direcciones para es gratis, esto no cuesta nada. Todas las direcciones las voy a proveer para que ustedes estén muy claros en cómo hacer, como todos los estudiantes anteriores lo han podido hacer sin inconveniente. Por lo demás, jóvenes, que tengan un excelente fin de semana. Nos vemos, Dios permite, el próximo martes en la noche. Hasta luego, jóvenes. Tengan una muy buena noche. Que pasen muy bien.
Gracias, profe.
Gracias, profe.
Muchas gracias. Una muy buena noche.